All right, let's continue with the chapter 3. In this slide, I'm going to be talking about the CPU switching between processes. If we're going to be processing or executing more than one process, whether we're talking about batch processing or timeshare, okay? And if you don't know the difference between those two, please refer back to chapter 1. We do something called context switch. What is basically context switch? It's the process of moving from the context of one process to another. So look what's going to happen here. We have two processes, P0 that is executing, and you have here P1. This is the line of execution of P0. This is the line of execution of P1, okay? So P0 was executing here, and then it made an interrupt or certain system call. Okay, so P0 will leave the CPU for P1 until, what it's waiting for occurs and then gets rescheduled. So what happens? We save the state into PCB0. What is the state here? The program counter, the process state, the registers, whatever else that the process depends on. Then after you save that, you load the state from PCB1. So you get the program counter of PCB1 and set the program counter with it. You get the registers and so on. How does it work? Let's assume that those are the data of PCB1. So the the program counter equals, let's say, 101. The AX equals 5. The BX equals minus 19. The C, and so on. Okay. So here is the program counter. You set it with 101. The register AX inside the processor, you set it with the value 5. The BX, you set it with the value minus 19, and so on. Why do you do that? When you set the environment with the moment that the PCB1 left, this makes the environment for PCB1 as if PCB1 never left. As an example, we have two students here sharing the same room for presentation. This one is presenting chemistry, so he has all the chemistry tools and stuff that is needed. This one presents whatever mathematics. Okay, so when that one was presenting, you have here everything that this one needed for chemistry experiments and so on and so forth. Before this one comes in, you're going to be removing all those stuff and set the room up again with the mathematics stuff. So when this one comes back, we'll find the room exactly the way that one left it. So as if this student never left. This is exactly what happens here with the PCB0 and PCB1. Okay, now that you saved PCB0, when the time comes for the PCB 0 to be loaded again, you're going to be saving the state of PCB 1. Why? Because all the changes that happened here get saved. Then you load the PCB 0 again, and so on and so forth. Of course, here you will see, it will execute again, and so on and so forth. This will happen until the processes get done from execution and they terminate or leave the system. So this is what we call context switch. So when the CPU switches to another process, the system must save the state of the old process. Why? Because if it doesn't save and then you load the old process again, it will execute from the very first beginning. So this means that this process that gets interrupted will never finish execution, because each and every time it gets loaded again, it will start again from the very first beginning, from line 0, okay, which doesn't make any sense. So you have to save the state of the old process and load the state of the new one. Why? To continue from where it stopped. Okay? Context of a process represented in the PCB. That's basically, the status that the PCB has. Okay? So the context switch time is pure overload or overhead. What does it mean? When I tell you the time you drive from where you live till you reach the university is an overhead. Why? It does not really contribute to the actual academic process itself, yet you have to do it in order to be in the university, to attend your classes and resume your academic process, right? So this is an overhead, okay? This is an overhead. And the word overhead also gives you the impression, which is very true, that, even though it's something that you don't get benefit of, so basically a waste of time, kind of, but it has to be done, okay, which also makes it not a waste of time. So it does not contribute to the actual process, yet it has to be done for the process to be successfully done. So the system does no useful work, okay, while switching, okay. What the author wanted to say here, that it does not actually contribute to any benefit that you get from any CPU cycles. So the CPU will be kind of idle when it comes to processing. But it has to be done. Why? Because of the multi-programming. Remember, what is multi-programming? Multi-programming is loading more than one process into memory. So in order for you to be able to execute those processes, you need to move from one process to another. Whether you're doing it batch or a timeshare, it still applies. You need to move from one process to another. So moving from one process to another requires the context switch, which is saving the old PCB and loading the new PCB. All right. The more complex the operating system and the PCB, the longer the context switch. I'm gonna be when we go for chapter 5, I will discuss the relationship between the context switch and the quantum that is being assigned to the process in the case of timeshare. Okay, because there is a kind of a relationship. I mean, there is something that has to be taken into consideration between those two. So the time depend on the hardware support. Okay, some hardware provides multiple sets of registers. okay, per CPU, multiple contexts loaded at once. Well, this is hardware. I mean, we're gonna be dealing here with the worst case scenario, which is that this one does not really exist, okay? As engineers, we always deal with hardware with the worst case scenario. Multitasking in mobile systems, as we have mentioned before. What is multitasking? It's actually when you share time among the jobs that you have or the processes that you have. And please do not, again, I cannot stress on this enough, do not mix between multi-programming, multitasking, and multiprocessing. Okay? It's actually very annoying seeing people mixing between those different concepts. So some mobile systems, okay, like early versions of iOS, allow only one process to run, okay, and the other get suspended. All right. Due to the screen real estate, user interfaces limit operating systems like the iOS, okay, to provide for a single foreground and a multiple background processes in memory running, but not on the display. So this actually allows here, as you can see, parallelism. Okay, so single foreground, so the one that you see, but you have multiple background running, but you cannot really see them. For Android runs foreground and background with fewer limits. The background process uses a service to perform tasks, and the service can keep running even if the background process is suspended. Anyhow, that's not really important here. What's important is that you can see that different operating systems deal with how the multitasking is in a different way. Okay. Having said that, you would see that the iOS and the Android are very different in how they deal with multitasking. Okay, so as I have mentioned here, you have the foreground process running on the screen. The other ones are on the background. This is for the iOS, and the older versions of the iOS used to suspend those, so one process at a time to run. For the Android, as you can see here, it runs both foreground and background. Okay, there's no problem here, and the background runs through a service, and the service keeps running all the time. Okay. So this is how we deal with multitasking. Of course, those things differ from a version to another. So the older iOS were much less capable of doing those. Okay, until recent actually. All right. Anyhow, what are the operations that we do on the process? Okay. As you can see here, we have a mechanism to create a process and to terminate a process. You would think that's very easy. No, it's not. It's not as trivial as it sounds now. And let's see. For the process creation, every process needs a parent to create it. So the parent process creates a child, or it creates children processes, which in turn create other processes, and so on. So in this case, you're gonna be building a tree. Look here, a tree of processes. So every process here has a parent. Every parent has a parent, and so on, until you reach the very first process, the Adam of the processes. Okay, the Adam of the processes. Every process, as you can see, has its own PID, unique. It's a unique PID. All right, so this is the tree of processes that we are talking about here. Okay, every process has its own PID. For any process to run, you need resources. Those resources could be CPU, it could be memory, files, or whatever. Okay? We have here a question, and the question is, where does the child get resources from? We have three different models. Okay, the parent is very generous, extremely generous. That's model number one. So the parent says, everything I have, I will share it with my children. Okay, so the parent and the children will share all resources that the parent has. Okay, the other one, the parent says, okay, I'll be sharing resources with my children, but not all the resources. I'm going to be allocating some resources to be shared and other resources to be for myself. And that would be model number two. So it's generous, but it's not that generous. The third one, the parent says, the same way I got my resources, my children will go and get theirs. So I'm not going to be sharing anything. I got those out of my work, out of my, I'm going to be keeping those resources to myself. The same way I got my resources, my children will go and get their resources, and that would be the third model that we see here. Okay? So this is the options of getting the resources for the child when the child gets created. Now, after the child gets created, how does it run? We have two options. The parent and the children execute concurrently. All right? The parent waits until children terminate. That would be the second model. Okay? So, basically, the first one would be like that. Here is the parent. The parent created two children. They will execute like that concurrently. The other one, the parent created children. This parent will wait until the children are done, and then the parent will continue from where it stopped. Okay, so the parent initiates children, waits until the children are done, and then continues. That's model number two. Model number one, the parent will initiate the children and they will work all together concurrently. So if the parent initiates two children, you will find three processes running concurrently. Okay? Now, the address space. Now here is the parent. The parent has address space. And the parent creates a child. We have two options. The first option, the child will have an exact copy of the parent. So what would it be? The same program, same everything. Okay? Same copy. So here is the child, here is the parent. That's child number one. The other choice, the parent will be, the child will be created, but it has nothing to do with the details of the space of the parent. So it will not run the exact same program as the parent. It will run a totally different program for it. Okay, so this one, you have the child having the exact same program, the exact same space. This one, the child would have a totally different space compared with the parent, because it loaded basically very new, like different program. Okay, so the question is, if you have a parent and the parent actually initiates a child, it's very simple to understand why would it actually initiate another program. The child will have another code. You want to perform something else, so you're going to be running another code. Yeah, that makes sense. Why would it initiate a copy of it? Okay, to speed up the processing. We will talk about that when we talk about data parallelism and task parallelism in this chapter, later in this chapter. Okay, so yeah, you can actually, the parent can create a child that is a copy of it to speed up the process of processing. All right, and this in Unix we use something called fork and exec. Fork and exit. What is fork? It's a system call, and I hope you guys know by now know what a system call is. What does this system call do? It creates a new process, fork. Okay, so when you call the fork, that's exactly what happens. Look, here is the parent executing, and then the parent calls a fork. When fork is being called, here is the parent and here is the child. That's why it's called fork, by the way. Okay, so this is fork. How about the execute? It's another system call, but it's used after the fork. So first you fork and then execute. Why? To replace the process memory space with a new program. All right, so if you want this child to be different from the parent, it executes a totally different program, then you call execute. Okay, and you give it the, as you will see later, the name of the program, and the program gets loaded inside this process. Okay, fork will create you the shell of the child. Okay, that has the code. It's a it's a duplicate of the parent. If you want to change that, then you're gonna really call execute with the name of the other code or program, and then this is gonna be loaded. The parent process calls wait to wait for the child to terminate. Okay. Look at that. Here is the parent. This is how you fork a child. PID equals fork. This is the system call. As soon as you call this, now you have two concurrent paths. The path of the parent and the path of the child. When the PID value is greater than 0, it means you're dealing with the parent. When the PID equals 0, you're dealing with the child. How about the negative case? Then there is an error happened while forking. Okay? Now, the child will execute something here. The parent will wait. Okay? Will wait for the child to finish. Now, the execution happens, then the child exits. As soon as the child exits, now the parent can continue execution. This is one of the models of how this happened. By the way, whether the parent will execute concurrently with the process, with the child or not, it has to wait in the end. If it doesn't wait, this child can end up being, or will end up being, one of two cases. Okay, if it doesn't finish before the parent, okay, either an orphan or a zombie, as you will see later. Okay, so parent and children have to be synchronized. And why does this happen? Because the parent is the one that is responsible for getting the resources back and so on. So if it doesn't do that, we will be having a problematic process as a child waiting for something to happen. Okay, here is the tree that we talked about before. Okay, and here is the code. Look at that. You include system/types.h, okay, the uni.h, and of course that's studio, the standard input output.h. You need those two to do forking. Here is the main. We define something called PID. It's the process ID, the unique one that we talked about. What is the type of it? Here it is. PID underscore T. Where is this defined? It's defined here in the types.h. Okay. Let's fork a child. Look. This PID that has been defined equals fork. What is fork? Fork is the system call. Okay, it's the system call. When you fork, you have two ways here. You see, you might say, oh, I don't see it in the code. Yeah, well, of course, because you have a program counter here that counts for the parent and another program counter that counts for the child, okay? If the PID has one of three values. Negative, 0, positive. I guess after Corona we all hate this word. So if it's negative, this means that there is an error happened while forking. So forking didn't work well. Okay, so you're going to be saying here, fork failed. Okay, and then return. So get out of the program. Okay, here. Okay, if the PID is not negative, then it has two possibilities. The possibility of 0, this is a child. The other possibility, which is the positive, this is the parent. So this is the code of the parent. This is the code of the child. Of course, you can write anything in the child. You don't have to have this. Okay? You can write anything here. So the child process, according to what is being written here, you will exec load program, exec LP, exec load program. Here is the ls, which is a command in Linux. You will practice that in the lab if you didn't already. And here is the command, and this is a parameter. It doesn't take any parameters, the ls in this particular case. That's why we're passing the null. All right. So in this case, okay, the child will list. ls in Linux is equivalent to dir in Windows, by the way. So it prints everything in the directory. Okay? It lists everything in the directory. So that's what the child does. The parent here, look, what does it do? Wait. So this program will output the following. All the files in the directory, given directory, and then it will tell you child complete. Child complete is being printed in the parent, yes, but you have here wait. So the parent will wait until the child is done its own code, and then it will continue the rest of the code. I hope this is clear. After we're done that, we're going to be returning 0, the main program, and that's it. I hope this is very, very clear. This is very important in order for you to program your project, the course project. You need to understand this code, because you're going to be doing this in the project. As we have talked about it, you need to do it either both with concurrent processes and with threads. Okay, we're going to be stopping here, and we're going to continue in the coming part.